right? So let's just look at this differential form and see, at least in one situation, it should be incredibly easy to work out. So let's look at the Laplace equation in one dimension. So if I have one dimension, if I have a one-dimensional situation, that means I have the x-axis only. And so instead of having this gradient, this del squared here, it's just a one-dimensional thing, so it just becomes a derivative, right? And so what this is saying is the second derivative with respect to x of the potential is going to be equal to 0, right? And so this is a differential equation, bless you. This is the differential equation, and so we should be able to figure out what is the potential, what is the v that will satisfy this differential equation, right? Okay. All right, sorry. Well, so you guys maybe could tell me here. If I have a function, forget about potential, forget about charges and electrons. If I have a function and I take its derivative or its second derivative, if I take a derivative of something and it's equal to 0, what was that thing that I took the derivative of? I take a derivative and I end up with a 0. What was it that I got?
Constant.
A constant, exactly. That's right. So in this situation, this is telling me that I have a second derivative and it's equal to 0. So that's telling me the first derivative, just dv dx, is equal to a constant, right? So we have this constant, and it could be any constant at all. I'm going to use the constant m, just because, for no particular reason. Okay, so now I have I've taken one order of a derivative away, and so now I can just do the same thing again. Sort of a simple way to do this is to separate out the dv and the dx. Don't tell any math people that we're doing this, right? You're not really supposed to treat a derivative like a fraction, but we're physicists, so we can do whatever we want. And so when you do this, now I just integrate both sides. And when I integrate the integral of dv, that's just v. When I come over here, m is a constant, right? We just said that. And now I have dx, integral of dx. And so when I take that, I get mx. What am I missing yet? When I take an integral that doesn't have bounds on it. If I take an indefinite integral.
Plus another constant.
Plus another constant, great, excellent. So I only need one constant. I don't need to do it on the left and the right. I only need one, and so I'm going to have that over here, and I'm just going to pick b. And so you can see here then that our v of x is equal to mx plus b, right? And that is telling us that the solution to Laplace's differential equation in one dimension is just a straight line, right? And so this also brings up another kind of important point about Laplace's equation, and really any kind of differential equation, is that because there was a second derivative, because we had two derivatives, right? We had two derivatives with respect to x, we end up with two arbitrary constants. Right? In this case, our arbitrary constants were m and b, right? So I have no idea what m is, and I have no idea what b is. However, I can determine what those arbitrary constants are. So we figure out values of m and b by applying boundary conditions. And so boundary conditions are just situations where I know the potential at a particular point. So for example, let's say in this situation, we just solved the Laplace equation in one dimension, and I was given, let's say we were given the boundary conditions. I don't want to write it that way. I was given boundary conditions. Maybe V at X is equal to 0 is equal to, I don't know, 4 volts. And V at X equals 2 is equal to, I don't know, 6 volts. I'm just making these numbers up, right? So now these are boundary conditions. We say that they're boundary conditions because they are restrictions at a boundary, meaning they're restrictions at a point in space. At a point in space, as opposed to an initial condition, which would be a restriction or a condition at a point in time. So for us, we're worried about boundary conditions in space on the x-axis because we've taken two derivatives in the x direction, right? So we need boundary conditions for the x-axis. And so now that I have my function, I have v is equal to mx plus b, I just apply these boundary conditions to figure out what my m is and what my b is. So let's say I do v at 0, that's m times 0 plus b is equal to 4. That means I can say right away that b is 4, obviously 4 volts, right? And then I can do the same thing again. V at 2 is going to be m times 2 plus b. Now b we already got done saying was 4, and we are told that that's equal to 6. Again, I've just made these numbers up. I'm just sort of showing that we can just plug these in to get our values, right? And so this then gives me 2m plus 4 equals 6. Subtract 4 from both sides, I get 2m equals 2, so m is equal to 1, right? And so now we have both our equation, our value of m and our value of b, and so v of x is really just equal to x plus 4, right? Applied to those boundary conditions.